Alright, am I live? Can I hear myself on the stream? Alright, am I live? Can I hear myself on the stream? That's fun. I can. Alright, we'll kick off in about 10 minutes. If anyone has any questions, either post them in chat or ask me them. Generally are the two ways that you can get your questions answered. All right, everyone, welcome back to COMP2521. It's Tuesday, it's 9 a.m. Chat, can you hear me? I'm going to assume chat can hear me. If they can't, they will yell at me at some point. People in the lecture theater, can you hear me? Yes, that's good. I'd be worried if that wasn't the case. Today we're going to look at sorting algorithms. We're going to do an introduction to sorting, but before we do that, I have a few quick admin things that I want to address. Did you know that 95% of the people that watch the lecture recordings are not subscribed? If you subscribe, I can turn off ads. Currently, the lecture recordings all have ads on them. If every single person that watched this lecture recording smashed that subscribe button, we'd be able to get 1,000 subscribers. And if every single person enrolled in the class watched the lecture recording, we could get 4,000 watch hours very soon. And once we do that, I can turn on monetization and get paid for those ads you see every 5 minutes. Alternately, I can turn the ads off. Currently, it's out of my control. So make sure, go to youtube.com, comp2521, smash that subscribe button, help us reach our goals, and what will I do? I'll do a giveaway. Is that what YouTubers do nowadays? I'll buy 1 Robux gift card and raffle it off to one of my subscribers. And it may not even be someone from this class. That's recorded now. If we get to the goal, I have to do it. All right, that's the admin with regards to please subscribe. The other bit is that I had some questions about where the lecture slides are because they're sort of in a slightly esoteric place. They are here. So if you click this link, then you can follow along with the slides if you want. That one was less exciting, but they can't all be winners. All right, what does chat have to say about this? Yeah, they can hear me. Awesome. All right, we're going to do an introduction to sorting algorithms today. As a recap of what we went over last week, we use big O notation to analyze our time complexities. That tells us how long our program will take to run, not in terms of seconds, but in terms of how it grows based on the input size. So we have time complexities like order n for when it grows linearly, n squared for when the square of the input is how long it takes to run, log n when the problem halves every time. We talked about linear search. Linear search has to check the items one after the other. Can someone tell me the time complexity for linear search? Order n, because there's no way to make it better because we can't tell for sure if that is going to be in the list based on the data, because the data might be in random order. We also learned about binary search. Who can tell me the time complexity for binary search? It's log n. Awesome, because we divide it in half every time. I did buy 70 chocolates, and I did the maths. There are not 70 of us physically here. So if you answer questions well, I can throw things at you. So who answered the log n thing? Who said that? Do you trust me? That's a no. You trust me. Okay, they trust me. Here we go. Do you like Cherry Ripe? Some people don't. Too bad. Aw, that was brilliant. Thank you. All right, so if you answer questions and you want one, I can arm cannon these at you. If you answer questions and don't want one, maybe I'll do it anyway. No, that's not good. The reason I bought them is because last week I talked about some two time complexities right at the end, and I got them slightly wrong. Under this more examples, we're approached. Who looked at this afterwards like I said you should? A few people. Who can tell me why this is log n? Yeah, we're doubling the increment each time, which means we're halving the amount of space left to search each time, which makes it log n. That was a team effort. I'm gonna regret this. Here we go. I'm so goated. I'm so sorry. Chat, look at what you miss out on if you don't come into class. And this one was, in fact, n squared. The relationship is a bit weird to explain, but imagine you have the number 9. Are you all imagining the number 9? All right, good. Well done. Then, the numbers that you need to sum to get to 9, if you add 1 plus 2 plus 3 plus 4, you surpass it. 4 is roughly 1.3 times the square root of 9. If we remove the 1.3, it's order square root of n. And that tracks approximately for all of the numbers. You look like you disagree with me. Feel free to mathematically prove it or go on the forum. All right, so we need to be sorting, and oftentimes, much like in life, we need to ask the question, why bother? I ask myself that every day. Sorting enables us to do searching faster. If we can't sort our data, we can't do a binary search on it because the data won't be in sorted order. It allows for better algorithms in general because if we can make good assumptions about the data, such as the fact that it's sorted, we can make better decisions about how we're going to choose our algorithms. If we don't know what the data looks like, choosing an algorithm is quite challenging. So if we sort it beforehand, then we can make better decisions. Things like finding duplicates and merging two lists are much easier if your data is already sorted, and sometimes they're impossible if the data is not sorted. When we sort, we perform it on a collection of some kind. Typically, this collection will be something like an array, but it could also be a linked list. I don't have any examples in my slides of sorting on linked lists, because sorting on linked lists is scary, and I think my live coding would fail. But there are examples on previous year's slides if you're super excited about the idea of sorting on linked lists. We can also do it on files, which are just collections of words. And we sort based on this thing called a key. The key is the element that we say we're sorting by. So things are sorted based on their key. So for example, if your key is just an integer, then what you sort on is based on if the integer gets bigger or smaller. So your keys could just be an integer. If you have a collection of characters, also known as a string, your key could actually be any character in that string, assuming all the strings are the same length. Typically, we sort strings based on the first character, but if you want to, you could sort strings based on the second character and have a really weird but still sorted array based on your criteria for what is sorted. Characters are generally sorted by their ASCII values. The key can be whatever you want. Let your imagination run wild. Be free. Don't feel constrained by numeracy or literacy. You could set the key to be how much the value is if you square it and then perform some other operation on it. The keys can be anything. Oh, wrong button. So we sort arrays of items. Our items is actually, so things such as ints, integers, strings, and structs. Structs is going to be a relatively important one later on. And again, these are sorted based on keys. So an array of integers sorted based on the key being the integer and being whether it is higher or lower. A list of strings based on the word, normally sorted alphabetically. Structs get interesting because structs have multiple components and we can decide what we want our key to be out of the struct. Hello. I don't believe you'll be accessing any files in the labs, and if you will, we'll give you code to start you off. The thing about, one of my big problems with C compared to other languages like Python is that opening a file makes me sad, and so I'd like to avoid doing that if I can. I certainly won't be doing it. So it can be sorted based on the entire key, or just parts of it. One or more field if it's a struct. So let's think about this more abstractly. Think about student records. You're all students here, I assume. Maybe you're just really big Henry Hickman fans, and that's why you're in the lecture. Technically, those two things are not mutually exclusive. You can both be a student and be a really big Henry Hickman fan. I've seen it happen before. But let's say our struct is made up of names and ZIDs. Talk to your neighbor about the different ways that you could sort them. Like, what are the two keys that you could sort by? What would they look like? Neighbor discussion friend time. What are some keys we could use? People saying in chat. Will we be tested on sorting linked lists? I'll be writing the test. All right. It's time to get pelted for answering my questions. Oh, you've got boost, which is my favorite. What's an example of how we could sort our student records? Alphabetically? Here we go. We got it, well done. Alphabetically on what though? First letter, first name, that's a good example. I saw hands here. Yep. Sorry, first number and then what? Yep, so you could treat ZID as a string and sort them based on the first number, then the second number, then the third. You could even sort them by the first character. It would be quite redundant though, because they're all Z. Does anyone know why it's called a ZID? Me neither. Okay, I feel like I need to defend myself really quick. I have one eye. What that means is I don't have depth perception, which means me deciding to throw chocolate in the audience wasn't smart. I didn't think this through very well. What other ways could we sort? Any other ideas? Yep. The sum of the ASCII values in the name, so people with really long or complicated names or names that is just get to be sorted earlier or later. Yep, that's a fun one. I see a name, I see a hand up there. Oh God, that's so far away. Okay, do you want a crunchy? I don't know what yep, up the back. Yep, I saw your hand. What was that? We could sort of reverse order. Reverse order based on what? Yep, reverse order based on name. Yep, we could do that as well. I'm just going to walk this one. There was no way. There was absolutely no way. Those are some examples of how we can do sorting. We're going to go over lots of different types of sorting algorithms. Today we're going to go over elementary sorting algorithms, things like selection sort, bubble sort, insertion sort, and an example of an elementary sorting algorithm is shell sort, but I'm not going to go over that. That's when you do insertion sort on shells and then merge them back together, and it's really cool, but that's not covered, so don't worry about it. But if you want to learn more about some elementary sorting algorithms, shell sort is a really fun one. I think they're all really fun, but I've been told that my opinions don't necessarily line up with the general population. We'll also do some divide and conquer sorting algorithms. This is where we get into that logarithmic type sorting. Things like quick sort, which you'll never guess pretty fast. Merge sort, which is a reference to the TV show Survivor when the two tribes come together and merge into one tribe. I think that's what it's named after. I'm not going to look this up. And we've also got non-comparison-based sorting algorithms. So all of the algorithms that I've just named are comparison-based sorting algorithms. They work by comparing keys. We can actually do sorting algorithms with non-comparison-based operations. So things like radix sort and a key indexed counting sort, which is also not covered, but if you're desperate for more sorting algorithms, as I know you all will be by the end of this class, then that is an option for you to go over. When we are analyzing sorting algorithms, it's a bit harder to say the average case. It's a bit harder to say I'm just going to analyze what the average case is, because I said before that you can do the best case plus the worst case and divide it by 2. That's not really true for sorting algorithms because they have special properties. That means the average case may be weirder, not just the sum of the first and the best and divided by 2. So what we're going to consider instead is what happens on a randomly ordered list, and we're going to sort of call that our average case, because if your list is randomly ordered, how your sorting algorithm performs is generally how it will be on average. We'll also talk about it in sorted order. So if your list is already sorted, how does your algorithm behave? If the answer is poorly, then maybe you should reconsider your sorting algorithm. Or maybe not, because a bit of a spoiler for later on, quicksort, which is named as such after John Quick, that's not true. It's named as such because it's quite fast, is actually really bad if the data is already sorted. Yeah, if the data's already sorted, quicksort sucks.
Oh, because it doesn't check whether it's sorted or not.
Yeah, it doesn't check, it just does its operations anyway. And we'll get into that tomorrow. Reverse sorted order. So if your list is in reverse, how does your algorithm perform? These are the three cases we'll consider to figure out our worst case, our best case, and our average case. We also consider the number of comparisons that are made. So how many times do we compare two items? And the number of items is the relation to which we compare it to. So if it is n items and takes 10 comparisons, 10 times n. We also talk about the number of swaps. So not only how many times do we compare two items, but how many times do we need to swap them around? And this will give us our big O notation for our sorting algorithms. Got a horse up there because it's stable. Thanks for coming to my comedy show. The properties of a sorting algorithm that we're worried about are whether or not the sorting algorithm is stable, whether it is adaptable, and whether it is in place. You may be thinking, Henry, what do these words mean? That's a great question. I'm going to answer it now. Stability is about whether or not the relationship of items with equal keys is preserved. Because there may be things like our structs, like our student IDs with their names and their ZID, and if we sort them by name, maybe we want to keep the original order of the ZID. Or imagine you're sorting a deck of cards. I wish I physically brought a deck of cards with me, but I didn't know how I'd do it on the live stream. And you have the 2 of clubs, the ace of diamonds, and the 2 of spades. When you sort them, you still want the 2 of clubs to be before the 2 of spades. It's important when sorting an array of multiple items with different possible keys, because that order may actually be important. It's not important if every single item has unique keys, because then it doesn't really matter, because they can't have that relative order that matters. And if the item is the key, we also don't really care about that. So stability is about if items of the same value stay in the same order after we sort them. Let's do an example of it. Consider the following array of whams and names. So we've got Alice with 90, Bob who has 75, Charlie who also has 90, Diana who has 75, and Eve who has 90. What would a stable sort, and we're sorting by wham, what would that look like? Talk to your neighbor real quick, and it's okay if you don't know, because I will reveal the answer later, because that's how this sort of lecturing thing works. But discuss with your neighbor what you think is going to happen if we're doing a stable sort. Have a quick chin wag. I'll see if the chat says anything. All right, good stuff. Hopefully you had fun with that conversation. An important thing in this class for me is not only do you learn, but you also have fun and make new friends. So I hope we've accomplished that task right now. So here's what the stable sort will look like. First will be Bob at 75. Then will be Diana with also 75. Diane, yeah. Then will be Alice with 90, Charlie with 90, and Eve with 90. The reason for this is that because Bob and Diana had the same wham, if we go back to our original array, it's important that Bob stays before Diana to preserve that original placing of how they were. That makes it stable. Bob must always stay before Diana, which also means Alice must stay before Charlie, and Charlie must stay before Eve. So this is an example of a stable sort. If I did an unstable sort, it may be that Diana ends up before Bob, or Charlie ends up before Alice, or after Eve. But because I've done a stable sort, they've maintained their relative position to one another. Are there any questions about stability? Yep.
For stability, if the certain program is stable, that means that will it run quicker, or will it just...
Okay, so a great question. If the program is stable, will it run quicker? No, it's not nothing to do with the speed of the algorithm, just how the data ends up at the end compared to how it was at the start. It does not make it quicker, it does not make it slower. It's just to do with how the data is preserved. Great question. Great question. I forgot for a sec. I don't know why I've done this to myself. Hey, you're welcome. Bob stays before Diana. Alice stays before Charlie. Charlie stays before Eve. Adaptability is about whether the sorting algorithm takes advantage of the existing order that we've given it. So if things that are nearly sorted are way quicker to sort than things that are in random order, then your algorithm is adaptable. Notably, it's not just the case that the algorithm is faster if it's sorted, it's if the shape of the graph changes. So if it goes from being n squared in random order to O of n in sorted order, the shape of the graph changes, that makes it adaptable. It could be n squared in both cases, but just be faster on sorted order. That is not adaptability. There is a difference. Are there any questions about adaptability? Is anyone familiar with Maharaga? He adapts. It's like that. It's not like that. There's also the concept of something being in place. You sort the data without any temporary structures. This is great if you are memory constrained, because it means that we don't make extra arrays for when we're sorting. Algorithms like merge sort only work because we make extra space to put the data into, and then we do our sorting, and then we put it back into the original array. But this uses minimal extra memory, and it prevents things like memory failures because we're only sorting in the one array that we were initially given. So that's the concept of being in place. Are there any questions about being in place? I'm in a place right now.
Oh, as in like we don't use, we don't make a separate array and start sorting by design.
Yeah, so with being in place, we do not make any separate arrays. We do not make any extra data structures. We just sort in the array that we were given. That's what it means to be in place. So if you're a embedded systems engineer, for example, and you're working on a chip that has 2 kilobytes of RAM, this is a farcical scenario, but a small amount of extra memory, then you'd want to make sure your algorithm is in place because you don't have that extra memory to work with. And so using an algorithm that's not in place may lead to problems. Again, it doesn't really affect speed. In fact, if an algorithm is in place, it's possible it's likely to be slower because it can't make that those extra helpers to work with. It's stuck just working with what we gave it, but that's not always the case. So we make a generic sort function with a swap function for when we swap things, and we use macros for our comparisons. The way that this looks is this is what the call to a generic sort might look like. It would be void, it would be sort, an array of items, or actually it's a type, a struct called items. It will take an integer low, which will be the start of the array, the first index of the array, typically 0, but when we get to divide and conquer sorting algorithms, it might be that low is halfway through the list because you've split it in half. And high, which is typically the final item, the final index of the array, but if we're doing recursion, high might be partway through the array because we're sorting a subset of that array. That's what I said. And this is the swap function, which takes an item, 2 integers, and swaps them around. Item is a type def based on what we are sorting. So if we're sorting integers, our type def would just look like that. It says our type def is item, and it just is an integer. If we're sorting strings, our type def might look like this, and then we just make an array of items. The reason we do this is to make it easier to substitute in different sorting algorithms. We don't need to worry about if we're working with strings or integers. It can just be called item. Sorting enrollment struct. So if we're sorting by, we'll talk about defining keys shortly, but this is what a struct for an item might look like if it were a collection of students with their name and the course that they're taking. We also use macros, which are a thing in C to define what sort of key we're sorting and define how it's meant to be compared to one another. So if we're sorting an integer, we have our type def of int being an item. We define our key. What this line means is it just means the key is the integer. A lot of your keys will look like this, but when we do things like structs, your key will be defined differently. This defines whether or not a key is less than another key. So we're saying that if we'll call a function called LT, which is short for less than, on A and B, and that performs the comparison of whether the key of A is smaller than the key of B. We do this for all of the different ones. Less than or equal to checks if the key A is less than or equal to the key B. Greater than or equal to checks if the key A is greater than or equal to the key B. Greater than checks if the key is greater than B. If we were sorting structs, though, it would look slightly different. Our type def would look like this, as I said before, but our key would say that our key is equal to the name value. So in this scenario, we're sorting our structs based on their name, not based on their course. And the reason we use these macros is because now instead of needing to go through, change all of our code, and go, okay, before I was doing check if A is less than B, but now I need to do check if the string comparison of the key and the second key is less than 0. Don't need to worry about that anymore. You can just still call that same LT function we talked about. You don't need to change your code in the slightest. You just need to change how you define your macros, and your sorting algorithm will keep working. This is checking the less than or equal to, greater than or equal to, greater than. All of this code, I do have code for this. It's already posted online. In fact, if we go to COMP2521, hopefully you are aware that under lecture resources, there's code. And I push the code as often as I can, as quickly as I can. Under 2.1, all of our generic sorts are here. So if I go to Visual Studio Code, so we have our swap function here. This swaps two items. It puts the item at index I in a temporary variable, then puts the item, then moves J to where the item at index I was, and then puts the item that was at index I back in J. That's how you swap them. Swapping without temporary variables isn't a thing in C, but this swap function works for every single sort no matter what you do. And let's quickly make, have I shot myself in the foot slightly by not? That's okay. I'll steal it from later. I'm going to quickly call my sort function on, what did I call it? I called it A0. How long is this? 0, 1, 2, 3, 4. It's 6 items long, index of 5. I'm not going to actually sort anything, but I'm going to show you how these comparisons work. So let's go if LT, LT A indexed by 0, which is, what's A indexed by 0 right now? Down here, 42, awesome. And 0, 1, 2, 3, 4, I'll go A indexed by 4. And I'm going to printf, my comparison worked, \n. So what I'm saying is, check if the item at index 0 is less than the item at index 4. If it is, we'll print something out. So I'm going to go clang generic sort int.c minus -o_prog. I have an error because why do I have an error? Because I haven't included Stadio. Let's try that again. Cool, so my comparison is working. The reason we do this is because if we have to constantly change based on our data type how we're calling our less than function, then our sort sort of falls apart because we're going to spend more time chasing around our comparisons than we are going to be actually sorting the data in terms of coding. This is just to make your job, as far as coding is concerned, slightly easier. Yes, makes writing these. Yeah, they work like functions. They return 1 if true, 0 if false. So they're just like using if statements. So yes, makes writing these sorting algorithms slightly easier, allows us to reuse these macros in different algorithms. So if I take my quick sort and paste it into my generic sort function, it will still work because all of the functions are named the same. If I change my data type from ints to structs, it will still work because they are the same comparisons. Lets us easily adapt what we are sorting. Now, is this done in industry? And this is a question I get a lot when I'm teaching sorting algorithms. Is this sort of thing done in industry? And the answer is not really. I've said many times this is a concept course. If someone wants to sort something and they are Google, they will probably just call sort because people a lot smarter than me have written much better sorting algorithms than what I'm going to teach you. But this is about understanding the concepts behind sorting, understanding what could be going on behind the scenes, understanding why you'd want to choose certain algorithms. I've said many times, I truly believe this to be a concept course to better understand how you should be choosing your algorithms. Yes, having a strong understanding of sorting algorithms is important for understanding how to best approach problems. In the future, you may learn that the sorting algorithm in the built-in sort library is actually not very good in some cases, and it may be better to work with a different sorting algorithm. Or it may be that you have a set of data that works really well specifically for insertion sort and your program doesn't have a built-in insertion sort function. Also, I've been told before that this course and these sort of analyses are great if you want to get a job, for example, at Atlassian or Google, because they ask coding interview questions that talk about things like time complexity and understanding what goes on at this sort of level. So as a quick summary for the introduction to sorting algorithms, they allow us to perform other tasks easier. There are three main properties. We have our stability, which is whether or not the relative order of items is maintained. We have adaptability, which is whether or not it gets faster based on the data already being almost sorted. We have whether or not it's in place, which is whether or not it uses extra memory or just operates all in place in that one array. And we're now going to learn and analyze some sorting algorithms. I know normally after the first set of slides I would go to a break, but I'm quickly going to check chat. We'll talk about sorting algorithms for another 15 minutes and then we'll have a break. What does chat say? How to make a stable sorting algorithm using recursion? That is a great question. You will learn a stable sorting algorithm using recursion tomorrow. I'll just show the feedback welcome screen for a second to feel like I've completed my slides. Elementary sorting algorithms. I'm also going to take I need a caffeine hit. All right, we're so back. Elementary sorting algorithms. We're going to learn about three: selection sort, bubble sort, and insertion sort. We're going to learn how they make comparisons, whether or not they are fast, how we will analyze them, how they behave on three different types of data, and I'm going to make you do them. I'm not going to make you program them, but I'm going to make you actually perform the steps of the algorithm, because I think that is the best way to get an understanding. So we'll start with selection sort. The way this works is we go through the list and we find the smallest element. Then we swap it with whatever the first element is. Then we go through the list again and we find the next smallest element. And we swap it with the second element. Then we go through the list again and we find the third smallest element. And we swap it with the third element. Then we go through the list again and we find the fourth smallest element. Then we swap it with the fourth element. Then we go through the list again, and we find the fifth smallest element. Who's sick of me saying this? All right, fair enough. Then we find it would be inefficient. It's not very good. But in order to learn, it's also sort of quite an intuitive one, and it shows that you can't just compare everything. We find the second largest element, we swap it with the second to last element, and then we're done. How do we find the smallest element? How do we find, from everything in the array, what has the smallest value? What do we have to do to find that? We have to go through all of them, compare it to every other element. Let's find out. Let's do some sorting. This will not be a quick sort. Stop for applause. Nope, all right. So this is going to point to the heavier box. So I'm going to compare this box this box. Which one is smaller? One on the left? Okay. And now I want to do the next step. Which box should I compare? Green? All right. Which one is smaller? The one on the left? Which one is smaller? One on the left? Which one is smaller? I didn't rig this. Which one is smaller? The one on the left? Should we just put the one on the left up there now? Do we reckon it's fine? No? Should we keep checking? Which one is smaller? The one on the right. Okay. Which one is smaller? The one on the left, it points to the heavier box. The one on the right. And which one is smaller? The one on the left. All right, so this is our lightest box. I've done it. I've found one. Now I need to find the second smallest element. Well, let's start. Which one is smaller? The one on the left? Well, we already know it's the red one. We haven't let the computer store that in any way. The computer doesn't know that. Which one's smaller? The one on the left? Which one is smaller? Can you tell I'm really padding for time? Which one is smaller? Which one is smaller? Which one is smaller? All right, so let's put this one back here, and we'll bring this one down here. All right, who wants to find the third smallest item? I see absolutely no hands. Anyone in chat want to find the third smallest item? Nope. Someone said doing the same comparison again seems wasteful. It is. Selection sort is not very good. How many comparisons did it take us to find the first smallest item? Actually, no. Let's find the third one and count how many comparisons it takes. How many items do we have here? We have 6. All right. First comparison. So we've done 1. Second comparison. Third comparison. Fourth comparison. Fifth comparison. So, for 6 items, it took us 5 comparisons. So how many comparisons do we think it's going to take for 5 items? 4 comparisons? 4 items? 3 comparisons? 3 items? 2 comparisons? 2 items? Do I need to do any comparisons if there's just 1 item left? No, because it will be the biggest by default. So in the first iteration, it took us n minus 1 comparisons, and then we did 1 swap. Didn't think I was doing that bad of a job. Put that on my experience report. N minus 1 comparisons, 1 swap. Because I didn't do it in that demonstration, but when we're putting the item at the end, what we should actually have done is swap it to first. Second iteration takes n minus 2 comparisons, and also we do 1 swap. Third iteration takes n minus 3 comparisons and does 1 swap. Fourth iteration takes, I was really hoping for like a raucous n minus 4 comparisons and 1 swap, but you know what? You were brave enough to try. That was the best throw so far, and it still almost missed. Last iteration, 1 comparison, 1 swap. The swaps may not actually happen. For example, it might be that the smallest item is already at position 1, but we would actually still call the swap function on 0, 0, and it would swap the item at position 0 with the item at position 0. You could make it so that it doesn't. You could put in an extra check that goes if low and high are the same, don't call swap. But there's no real point in doing that. Swap's relatively inexpensive, and the comparison costs about the same as the swap does. So it's up to you if you want to do it that way. So for 5 items, it takes us 4 plus 3 plus 2 plus 1 comparisons. For 6 items, it takes us 5 plus 4 plus 3 plus 2 plus 1 comparisons. This can be turned into a formula of sorts. You may have come across it before. Quickly chat with your neighbor if you know what the formula is or if you can derive it really quick. I'll give you a minute as I chug more Pepsi Max at 9 in the morning. Right, so, does anyone know the formula? I've heard from you a bunch, I'll come over here. N times n minus 1 over 2, perfect. Here we go. No. My hero, thank you. Yes, n times n minus 1 over 2. You may think, Henry, that formula looks ugly. I spent hours trying to get it to not look like that. But this is what it is. N times n minus 1 over 2. So for 6 items, 5 plus 4 plus 3 plus 2 plus 1 is equal to 15, which is equal to 6 times 5. What's 6 times 5? 30. What's 30 divided by 2? 15. Cool, we've done it. 6 times 5 divided by 2. Notably, expanding our equation, if we go back to year 10 algebra, I think it would be, we get n squared minus n over 2. This is a formula that we can simplify for the purpose of time complexity. What does this make the algorithm? All right, he seems eager. What is it? N squared. I'm getting better, sort of as a person. Yes, it's order n squared. It is order n squared. Do we think it changes based on whether our data is sorted or not? In any case, is there any case where this changes? No. There's no case in which this changes because we're always doing the same operation. We're always searching through everything, looking for the smallest, and then searching through everything, looking for the second smallest. If it's on a sorted list, a reversed list, or a random list, no matter what, it will always take n times n minus 1 over 2 comparisons. Hello?
Would it change the n equals 0?
0 times minus 1 over 2, I think, evaluates to 0. But I might not. Pretty sure it does. No, 0 times minus 1 over 2, no, you can divide 0 by things, you just can't divide by 0. Yeah, it's already sorted. So your question of does it work for 0 is similar to does it change for 1? Because with one item, it's already sorted, and then 1 times 0 over 2 means we don't need to do any comparisons or any swaps. So it's still technically n squared. It just doesn't, it's just n squared on 0. Remember, n squared is not about any singular case, it's about how it grows as the input grows. But it's a great question, and I enjoy it. So, talk to your neighbors real quick. Do you think selection sort is stable or unstable? Nope, that's not what I said on the slide. Never mind. I thought I had those words swapped around the other way. What do you think? Oh yeah, probably. I think it might be as well. I have a hint. Yeah, if 2 large items are at the front, there's no guarantee they will be in the same order at the end, because they will get swapped all around, and they may end up in different orders based on how our data is sorted. For example, this 6652, the first iteration we would swap it, and the 6 at the end would be swapped with the 2 at the end. I should have color-coded these 6s to make it better, but the 6 at the end, the 6 at the front is swapped with the 2 at the end. Then, the 5 in the middle is swapped with the 6 in the second position. And then we actually do another iteration that doesn't do any swaps. And so the 6s have ended up in different orders than they were at the start. So this is not a stable sorting algorithm. It is non-adaptive because it always does the same thing no matter what the data is. It does not adapt. But it is in place. We do not make any temporary arrays. We do not make any temporary... question at the back? Yeah, sorry, question in the middle. Mm-hmm. This is true.
It's kind of, even though it's kind of backwards, it doesn't actually change anything, where it's saying like the number of powers between the divided number is flipping the two keys in a different order, even though the keys are equal.
Yeah. So,
If it kind of switches the order only in that setting, I don't know, is that actually like,
okay, great question. Great question. What I believe you're asking is, does it actually matter that it's unstable? Those sixes have the same value. Why do we care what order they end up in? Yeah. In some cases, it's fine for an algorithm to not be stable. There are lots of algorithms that aren't stable, and we're fine with that. It's just that there are some specific scenarios where you do care about the original order of your algorithm, and you do want it to be stable. So again, it's about understanding what sort of scenario we're in, and whether stability is a trade-off we're willing to make. With this data right here, it's fine that it's not stable.
and that scenario would only occur if the key wasn't necessarily equal to the original thing, is that right?
I'd have to think a bit more about it, but it may be right that sometimes they would end up in the right order. But we can't know for sure. Yep.
Will the, like, as you showed in the example before, you're going from left to right. Does that order matter?
So you could do selection sort in the other order, going right to left if you wanted. It would still do the same thing. You could also sort it in ascending or descending order, but it's about the comparisons that are performed, not necessarily the direction in which we do them in or what we're trying to get at the end. Yep. Sorry, I've got to first help people with chocolate. I'll walk that one soon. Sorry, what was your question again?
Can you give us some examples for like what would cause that stable?
What would cause this to be unstable?
Like I mean like what problem, like root
Oh yeah, real world problem. So for example, there was the names and ZID struct earlier, where your names may already be closer sorted, or you care for some reason that the names stay in the same order when you sort it. So if you sorted by, names in WAM I mean, because it might be, for example, that we just pick the first WAM with the correct value to receive a prize. And so the original order might matter for that, or it might not. Does that sort of answer? It depends. If we use a struct, there are lots of different keys, and so we may want to really care about the original order of those keys, because that may tell us something about the data. Yeah, cool. Happy with that? Or is that that's not a hand, that's just sort of a looking. Good question. Oh, man. Good question. Hey, you're welcome. It's not adaptive. It always performs the same regardless. It just does the same n times n minus 1 over 2 comparisons no matter what. And it is in place because we don't make any extra arrays to do our sorting. And I've noticed that I've not shown any code yet. This is what the code for selection sort looks like. It starts from low, it works its way up to high, it checks if the item, it goes through, checks if the item at index j is equal to the current minimum item we've got so far. If it is, it sets our new minimum item to the one at j, and then at the end of the second loop, it swaps them. You'll learn more about this code and you'll do some analyzing on it, but one thing I want to ask is, what is it about this code that lets me look at it and say n squared? Hello?
Should we like memorize it how to do the insert sort, or should we
Do you mean in terms of should you memorize how to implement them? My hope is that you won't need to memorize how to implement them, because you'll have a good understanding that if I said to you, implement it, you'd have a pretty good idea of how to get started. But practicing implementing once you have a good understanding is a great method. What is it about this code that lets me say that I can pretty much tell it's n squared straight away? Yep. Yep, a nested for loop inside a for loop. What about that nested for loop inside the for loop? Because the second for loop could theoretically just be 1 every time. If like it isn't here, but I could have a for loop inside a for loop and have the second for loop just be 1 if I wanted to. Did you ever? Okay, it's the fact that the for loop goes from all the way from where we start up to high. The fact that it's going up to n, and it's getting smaller each time, but it is doing n times n minus 1 over 2 comparisons. It's not a constant value, it's a value that is large and changes. So we can see that it's n squared. You've got the loop within the loop, and both of those loops are related to n. All right, so that is selection sort. It is now time for a small break, maybe 10, 15 minutes. I'll say 10, and then I'll look at chat to answer any questions, and then we'll talk about bubble sort. All right, raucous excitement. I'm setting the timer for 10 minutes. We'll come back shortly. I had chocolates more to give out. If anyone has any questions for me, I'll be at the front of the class. I'll also be here if you don't have questions for me. My position is not determinate based on what questions you have for me. Hello. Yep. One sec, I'll mute the stream, and I'll mute my microphone. Chat, we'll be right back. All right, chat. All right. Do we cover any randomization or shuffling algorithms? I cover rand briefly tomorrow to show what it does, but we don't cover our own randomization algorithms. All right. Bubble sort. Yeah. I know her. Right. Welcome back, everyone, to COMP2521. Let me just ready my cannon. You may think, Henry, how many bags of chocolate did you buy? That's a question for my accountant. Leave me alone. Now, bubble sort is the first ever sorting algorithm that I learned as a 14-year-old. That will not be on the exam. You don't need to know that. Everything else, who knows? No. So bubble sort moves from left to right. So it compares two items going from left to right. It can go from right to left, but it typically goes left to right. If they're not in order, swap them. So if a bigger number is before a smaller number, swap them. Elements are bubbling up to the end of the row. You may think this algorithm was named after John Bubble. No, it's named after the fact that the items bubble up to the end of the array. What was that, sorry? All right. Leave it to the professionals. No, I'm kidding. Stop if we don't do any swapping. So if we don't make any swaps, we're done. Technically, this whole extra swapping step makes it a modified bubble sort. Pure bubble sort would just go even if it didn't make any swaps. So if you're looking at bubble sort in a textbook or something, you may come across one that doesn't do this last step of checking if we've made any swaps. So the person who talked about doing a bunch of redundant comparisons, this is to prevent us from doing that. All right, we're going to do it now. I'm making your life better? Worse? Oh wait, I should make a, actually no, let's reshuffle the weights. All right. Which one is heavier? So they're in the correct order? Cool. Which one is heavier? Are they in the correct order? Nope. So I'll move this one. Oh no, yeah. Which means this one goes here, because orange was originally here. What I should have done is put orange back here. So now I'm going to put orange here to show that we've done the swaps. So now I'll bring orange down. Which one's heavier? Left, so we're going to bubble orange up again. Nice, now we'll do the comparison again. Which one's heavier? Orange, so we're going to bubble up again. And now which one's heavier? All right, we'll bubble it up again. And now which one's heavier? Green, so we don't need to swap them. And now last, for this step, which one's heavier? Green, so we do swap them. And so we've found out green is the biggest. This is looking a lot like selection sort, but there are subtle differences. So let's do it again. Which one of these two is heavier? Cool, so we need to swap them. Oh. And we'll compare again. Which one of these two is heavier? Right, cool, so we don't actually need to swap them. Which one of these two is heavier? So we do need to swap them. Which one of these two is heavier? So we do need to swap them. Which one of these two is heavier? Cool, so we don't need to swap them. I'll move this one into here. And which one of these two is heavier? Cool, so now we know that orange is the second heaviest. Again, this is still looking a lot like selection sort, but now we can go again. So we know that right is heavier. We know that right is heavier, so we need to swap them. Yep. We know that right is heavier, so we'll swap them. We know that this one's heavier, so we won't swap them. And we know that right is heavier, left is heavier, so we'll put them here. Okay, we've got these three that are definitely in the right order. Can I stop now? Or do I need to keep going because the computer's not done all of the comparisons yet? Keep going, we can't stop yet, even though three are in the right order. Oh, that one's heavier, so we don't need to swap them. This one is heavier, so we do need to swap them. Just a question?
So, like, now that we know what's your like
Yep.
how the system order so we can stick and just do the event?
So we don't actually fully know that, because for all I know, that box right at the end might be really light, because I haven't actually compared it to anything at the front yet. So the stuff at the end hasn't been compared to the stuff at the front. Some of the stuff at the end hasn't been compared to the stuff at the front. Points to the heaviest. And that one's the heaviest. All right. So for example, this box here might be lighter than this one here. We don't know yet. All right. Oh, for example, we hadn't compared these two yet. All right, this one's heavier. This one's heavier. And now we had to do a swap, so we'll do another set of comparisons. That one's heavier. That one's heavier. And now this one's heavier. Because blue and purple, sort of light purple, hadn't been compared yet, so we couldn't have known. Let's do more comparisons. So I'm still, my finger's getting sore from doing this. But boy howdy, what a great learning. Oh, we didn't do any swaps. No swaps occurred. Yippee, we're done. Because no swaps occurred, I can stop now. Can I hide that second row? Can I check order? I'm going to drag them all down here and check that order now. Just for the sort of satisfaction of being really good at sorting algorithms. Let's go. Right, so the items that are biggest bubble up to the end, and if we don't do any swaps, then we can stop at that point. So for example, this is just me going through a bunch of comparisons. We'll compare 4 to 3. Do I need to swap them? Yep, cool. Now we'll compare 4 to 6. Do I need to swap them? Nope. We'll compare 6 to 1. Do I need to swap them? Yep. We'll compare 6 to 2. Do I need to swap them? Yep. We'll compare 6 to 5. Do I need to swap them? So now we can lock in green at the end is our biggest. After one pass, 6 is in the correct spot. But we're not done yet. Compare 3 to 4. Don't need to swap them. Compare 1 to 4. I do need to swap them. Compare 4 to 2. Got to swap them. Compare 4 to 5. No swaps needed. Now we know both 5 and 6 are in the right spot after the second pass. Compare 3 to 1, swapped it. Compare 3 to 2, swap it. Compare 3 to 4, don't swap it. 4 is locked in. 1 to 2, no need to swap. 2 to 3, no need to swap. No swaps were done. All of our items are in the correct order. Bubble sort is done. Hello. No. Once we've put an item in its spot, we don't look at it again. We're like, I know you're the biggest. I know you're there. So I don't need to worry about that. I genuinely thought that was going further. Are there any other questions about this bubble sort and how it's working so far? Is there an understanding that things are bubbling up? Yep. Yep, when there's no swaps, that's when we end. All right, he doesn't want to get hit. I understand. No swaps were needed, therefore we can exit early. As I said, in traditional bubble sort, we would do more comparisons, and there would be more comparisons done. Any questions? So what's the best case scenario for bubble sort? Talk to your neighbor briefly about the best case scenario for bubble sort. Cool, so what's the best case scenario? It's already sorted. If it's already sorted, then we'll go through the list, we'll make no swaps, and we'll be done, because it's in sorted order already. List is already sorted, we make one pass, and then we are done. This is a list, it's sorted. How many comparisons does it take me to find out? I had someone say 5, and that's true, because we compare 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and we're done. Specifically, that is n minus 1 comparisons if it's in sorted order. So bubble sort, in the best case, is order n, which is like pretty quick. That's pretty fast. However, how often does the best case happen? Not very often. It's only if it's in sorted order. What's the worst case scenario, do you think? Yep, it's order n squared, but... Sorry, I heard someone talking about the data. Yeah, what's the data look like in the worst case? Yeah. If the list is in reverse order, I need to do, on my first pass, I need to do n minus 1 comparisons to get 6 into the right place. On my second pass, I need to do n minus 2 comparisons to get 5 into the right place. On the third pass, I need to do n minus 3 comparisons. On the last pass, I do 1 comparison to get it in the right place. In the worst case scenario, it is n times n minus 1 over 2 comparisons. That seems very similar to something we've talked about already. Seems very similar to selection sort. What's the big O notation for n times n minus 1 over 2? It's O(n) squared. So bubble sort in the worst case is order n squared. In the worst case, every comparison means we need to perform a swap as well. Now in the average case, figuring this out is a bit tricky. It is order n squared. You can derive that on average, bubble sort must perform 0.25 n times n minus 1 swaps. I will not. I will not be deriving this. But you can. But this is order n squared, because we drop all of the constants, you get n times n, that is n squared. We can also do it empirically, but not meant to say but, we can generate random lists and we can sort it a bunch of times and we can time it and we can see that it is still order n squared. That's a fun programming exercise that you can do in your own time. I do recommend it if you want to play around with sorting algorithms and play around with timing. So who thinks bubble sort is stable? Nice. Does anyone want to tell me why they think it's stable? Yep. What was that, sorry? Yep, so it's comparing between adjacent elements. And is it ever going to swap 2 elements if they're the same value? Yeah, so it'll check, but it's not going to swap them if they're the same value, which means that the relative order is preserved. Does that make sense? If I compare 6 and 6 in my bubble sort, I'm never going to swap them because they are the same. There's no reason to swap them. Therefore, it is stable. Comparisons are only made between adjacent elements, and they're only swapped if they're out of order, which means the relative order is preserved. Do we think it's adaptive based on what we've said so far? Yes? Yes, it's order n if the data is sorted, it's order n squared if it's not. That is the type of adaptiveness. Is it in place? Yes, it is in place, because we do not make any extra arrays. Who wants to see code now? Code. So we make a Boolean to check if we're swapped or not. We go through, again using that loop within a loop. If the item is greater than the item next to it, that's what the items j compared to j plus 1. We're checking the item next to j. If that's the case, we're swapping them, and we're saying we have done a swap. If we haven't swapped, then we break, and our list is sorted. Let's see this in action. I realize I should have shown this off in action for the last one as well. Well, first here's selection sort. The code is available. I've got my type def for ints. I have my swap function. I have my selection sort. What I've also done for selection sort is I've added a wee comparison counter to count how many comparisons it's going to take. So this list, 1, 2, 3, 4, 5, 6 elements, how many comparisons is that going to take for selection sort? Clang, selection sort. How many comparisons do we think it's going to take? Selection sort, 6 items. N times n minus 1 over 2 gives us 15 comparisons for selection sort. And no matter what, it'll be the same formula. But bubble sort, which is a different algorithm, I'm also going to put in a comparison counter. I'm going to go int comparisons equals 0. Have I misspelled? I have misspelled comparisons. Where should I put my comparison counter? I'm going to put it here. The reason I put it above the if statement is because I want to count both successful comparisons and unsuccessful comparisons. If I put my comparison counter inside the if statement, it would only count comparisons that lead to swaps. By putting it outside the if statement, I'm counting comparisons that don't lead to swaps as well, but are still performed. So now I'm going to printf that took %d comparisons \n comparisons. So this is a list that's in random order. I'm going to go clang bubble sort -o prog /prog. And that took us 15 comparisons. Interesting. 1, 2, 3, 4, 5, 6. I've somehow made one that also performs worst case. Let's rearrange our data a bit and see if we can get something different. Let's do 7, let's put 42 here. What have I done? Let's see if I put 1 at the start. Okay, phew. I was worried for a second that I just somehow accidentally coded insertion sort a second time. The order of our data matters. It makes a difference on how many comparisons we perform. If I put this in fully sorted order, 1, 2, 34, 42, 98. How many comparisons do we think this one should take? 5 comparisons, because we didn't do any swaps, we just went through the list, and it was sorted. One thing that I wanted to show off earlier is that with our type defs up here, this means that I can paste my bubble sort code into any other generic sort. So if I copy bubble sort, Command C, and I quickly open my generic sort of structs, and I paste my bubble sort in here. I was hoping I'd have some data in here. I'll need to include Studio and the standard library to get my booleans. Maybe booleans aren't included in the standard library. I can't remember where do booleans come from? When a mother and a father boolean love it. Yep, question here? Mm-hmm. Yep. Okay, so we said earlier that just because an algorithm performs better doesn't necessarily mean it's adaptive, so why is bubble sort adaptive? So things can perform better and still have the same time complexity. So there are some cases where sorted order performs better, but it's still order n squared. Because bubble sort changes from being n squared to being order n, that's why it's adaptive. The shape of the curve changes if we're in sorted order. So if we're in sorted order and we keep increasing the number of elements, it grows linearly. If we're in random order and we keep increasing the number of elements, it grows with the square of our input. These are different shaped curves, therefore it is adaptive. Does that make sense? It's a great question. I'm so goated. Okay, what part of this code lets me intuit that it's n squared? What can I look at? The for loops. What about the for loops? Yep. Yes, so they go from high to low and they go up. They go up from high to low, and it gives us that n times n minus 1 over 2 comparisons. Last up we have insertion sort. This is our last sorting algorithm of the day, and it is the best one so far. However, this is a very low hurdle. The way insertion sort works is we take the first element and we say you are a sorted array, because it is. Is a one element array sorted? Do we agree that a one element array by definition is sorted? Because this is a very important thing to agree upon for insertion sort to work. A one element array is sorted. Take the next element and we insert it into the correct position of the sorted array. This is done via comparisons and swap, and this increases the length of that sorted array. The reason this becomes powerful is that once we make a comparison and we don't do any swaps, we can stop, because we know that it won't go any further into the array because that part of the array is already sorted. I'm going to show this off because I think that wasn't a great explanation. So I'm going to say this is sorted. This is a sorted array. In fact, it can go down here. So now I'm going to compare it to here. And this is heavier, which means we do swap them. And now these two elements are a sorted array. So I'm going to come down here and compare it to this. This one is heavier than this one. So I can add this and say, okay, now these three are my sorted array. Because I know that this is heavier than this, I don't need to compare it to the green box. Sorry, I mean, I know orange is lighter than purple, so I don't need to compare it to green, because I know green is heavier than purple. Purple is heavier than orange, therefore green is heavier than orange as well. So now I'll compare green to purple. Green is heavier, so I will swap them. I'll compare purple to sort of purple as well. That is heavier, so I will swap them. I'll compare purple to orange. That is heavier, so I will swap them. That was the worst case scenario, but now we have 4 elements that are in a sorted order. Now I'll compare green to blue. Green is heavier, so I will swap them. Compare to purple. Purple is heavier, so I will swap them. Compare to orange. Orange is lighter, so I will not swap them anymore. So again, blue does not need to be compared to the purple at the front, because blue is heavier than orange. Now I'll compare it to red. Red compared to green. Green is heavier, so I'll swap them. Red compared to purple. Ooh, purple, red is heavier than purple, so I don't need to do any more comparisons. We're done, because everything to the left of red is lighter than it, because it's lighter than purple, because our array is already sorted on that side. Compare green to green. Green is heavier, so I'll swap it. This one's heavier, so I'll swap it. This one's heavier, so I will swap it. Ooh, do I swap them? No. So do I need to compare this green to the purple or to the orange? Nope, so I'm saving myself some comparisons due to the fact that this array, which has been slowly growing, is already sorted. Now last up, sort of pink to green. All right, I'll swap them. Compare it to red, I'll swap them. Compare it to purple, I'll swap them. Compare it to light green, I'll swap them. Compare it to blue, I'll swap them. Sometimes you get hit with the worst case. Ooh, don't need to do that last comparison though. So that took me 20 comparisons. Let's see if I'm right. We're so back. So insertion sort saves us some comparisons by assuming, or not assuming, by knowing that the elements to the left will be lighter once we've compared them. Are there any questions about how insertion sort works? I feel like I've gone less in depth on this one, but I will do another example on the slide. Yep. Does it matter what element we choose at the start? For simplicity's sake, you could swap any element at the start if you wanted to, but we'll just choose the one on the left and say this is a sorted subarray of my current array. If you want to make it a random element and put it in the left, you can, or you could start at the right if you wanted as well, but it's easier to just start from the left. It won't make a difference because we don't know what elements are in our array. We don't know what they are. Yep. That's also. Well, you could do a bubble sort that goes right to left and bubbles down. And it's the same with here. It's just the nature of the comparisons that makes the difference. For implementation, please do just follow what I've said, because you'll get yourself into a bit of trouble, not literal trouble, but just a bit tangled up if you try to do it other ways, and you won't have as good of references as what I'm providing here. Were there any other insertion sort questions? Relatively happy so far. Cool beans. So, we have our array, looks like this. 4's sorted as far as I'm concerned. It's in the right spot. It's, as far as 4 is an array of itself, looks good to me. I'm going to compare it to 1. They're not sorted, so I'm going to swap them. And now 1 and 4, I have a sorted subarray of 2 items. Things are moving up in the world. I'm going to compare 4 to 7, because 7 is our first unsorted item, and 4 is the last element of our sorted subarray. I don't need to swap them, so I can say, cool, 1, 4, 7, that's a sorted subarray, and it is a sorted subarray. I'll now compare 7 to 3, and I will swap them. I'll compare 4 to 3, and I will swap them. I'll compare 3 to 1, and I won't swap them, which means we are now in another sorted subarray of 1, 3, 4, 7. I'm going to compare 7 and 8. Am I going to swap them? No? No? Do I need to do any more comparisons with 8? Not right now. I have a new sorted subarray, 1, 3, 4, 7, 8. I'll compare 8 to 6. Do I need to swap them? Yep. I'll compare 7 to 6. Do I need to swap them? Yep. I'll compare 6 to 4. Do I need to swap them? Nope. Now I have a new sorted subarray, 1, 3, 4, 6, 7, 8. I'll compare 8 and 5. Do I need to swap them? I'll compare 7 and 5. Do I need to swap them? I'll compare 6 and 5. Do I need to swap them? I'll compare 4 and 5. Do I need to swap them? No. I have a new sorted subarray. It's called insertion sort because for each element that's outside of our subarray, we are inserting it into the correct position. Lastly, for 2, I compare 8 and 2 and I swap them, 2 and 7 and I swap them, 6 and 2 and I swap them, 5 and 2 and I swap them, 4 and 2 and I swap them, 3 and 2 and I swap them, 1 and 2 and I swap them. That was the worst case scenario where I did have to compare every element to every other element. However, I had to compare 2 to every other element, I should say. That took me n-1 comparisons, but there were so many other cases where that didn't happen, and so I should be thankful. I have a sorted array now, based on insertion sort. What's the best case for insertion sort? Discuss with your neighbor briefly. All right, do we have any thoughts? Someone said order n. Someone said sorted. Sorted is what I'm looking for. If the array is already sorted, yep. Someone said that if it's sorted already, I don't need to do all of this. I do need to check if it's sorted first, because I can't, I have one eye, so I can look at this array and I can go, yeah, that's sorted, but the computer has 0. I'm up on the computer as far as eyes are concerned. Yep. No, that's the worst case, but we'll get to that shortly. The best case is sorted order, because for every subarray, we only need to compare it to the last element of the subarray. And so we're only going to do n minus 1 comparisons, and then we will be done. So that becomes order n. Worst case, you just said it. Reverse order, because every time inserting the first element will take us 1 comparison and a swap. The second element will take 2 comparisons and 2 swaps. The third element will take 3 comparisons and 3 swaps. The last element will take n minus 1 comparisons like it did before when we were comparing 2. We had to go all the way through our sorted subarray. Oh look, it's back. N times n minus 1 over 2 is the maximum number of comparisons insertion sort will take. Oh, we're so back. What's this as an asymptotic time complexity? Order n squared. Order n squared. Wow. I meant to say that in the average case, it's also order n squared, and it's the same reason as bubble sort. We can show it empirically by timing randomized lists. I won't. Insertion sort. Do we think it is stable? Yep. Insertion sort is stable. Elements are only swapped if they're not equal, / if they're less than, and therefore elements that will have their order preserved. They're only swapped if they're out of order, therefore elements that have the same key won't be swapped, therefore we have stability. Do we think it's adaptive? Yep, it goes from order n squared in the worst case to order n squared in the worst case to order n in the best case. Do we think it's in place? It is in place. When I talk about a subarray, it's a metaphorical subarray. It doesn't actually exist, so I should be clear about that. That subarray that I'm talking about is just a metaphorical chunk of our first array. We're not actually making a new subarray. With swaps. With the swap function, with our code. Yes, this is what the code for that looks like. Code's not that exciting to look at. But what is it about this code that lets me say, oh, that's n squared? What is it? What can I look at? The 2 for loops. You may. Mm-hmm. Okay, so this is a great question. I said reverse order is the worst scenario, and I've been asked if the list is in reverse order, we can just go the other way, and then it will be order n again. The problem is, with our data, we'd have to know that our data is in reverse order to do that. And so if we did know that, then we could do that, but sometimes we don't know, and we just think that it probably won't be, and therefore we choose insertion sort. Let's look at insertion sort. Some code here. I'm going to do another comparison counter for you. We'll go int comparisons equals 0. This code has perplexed me. Where are my comparisons? All right, let me just run this real quick. It does end up in sorted order. This for loop only runs while the item is out of order. So this doesn't actually do an explicit if statement to check. The for loop implies that they are out of order, and the for loop will terminate if it's in the correct order, if it comes across a condition where it doesn't match. This is code from last year's instance of the course. I might rewrite this to actually have an explicit if statement, but let me know in the feedback if you like how that code is compared to the code with if statements and swaps. Here's a quick summary of the different time complexities and whether they're adaptive or in place or stable or not. Now, if insertion sort and bubble sort have the same time complexities, does it matter which one we choose? Quickly chat with your neighbor about whether you think it matters which one we choose. They have the same time complexities. Bubble sort and insertion sort are both order n in the best case and n squared in the average and worst case. So does it matter at that point? Have a wee chat. Right, does it matter? It does actually matter. Big O notation only tells us how the curve grows. And so it's not great for comparing two algorithms for the exact same time complexity. Bubble sort, as we saw the first time, makes many redundant checks that insertion sort doesn't have to do. Insertion sort doesn't check things that have already been checked or that it doesn't have to check. Bubble sort, we made a bunch of checks we'd already done before when we were bubbling up. If you don't believe me, do bubble sort and insertion sort by hand on paper with a deck of cards. I know, I've said it so many times, I'm going to keep saying it. I know this is a coding, you like coding, you're here to write code, but physically writing out the steps for this, physically doing them with cards, gives you such a great mind memory. I was going to say mind-muscle connection, that's a gym thing, but it does give you such a great idea of how it works physically, how you manipulate it around, and that is perfect for learning and understanding. And with these sorts of algorithms, you can do it. The algorithms we're going to talk about tomorrow are a bit harder to do with decks of cards because they only really show their improvements when you get to lots and lots of items. But for now, this is a great way to work with these algorithms and to understand what's going on. Also, count the comparisons on really large data sets with insertion sort and bubble sort and see how they differ. Do some work on your own. I've given you some boilerplate code. Play around with it and have fun. We are 10 minutes until the lecture officially ends, but I do like leaving the last 10 minutes for any questions. If you have any questions, you can raise your hand or you can come see me. And also, I have a bunch of chocolate still because I thought more people would show up and ask questions. So if you want some, just come and get one. Thank you very much, everyone. Thank you, chat. I'll also answer questions in chat. Oh, is Stalin sort faster than BOGO sort? Okay. Real quick, there is a sorting algorithm called BOGO sort. The way it works is it randomizes the list and then checks if it's sorted. And then it tries it again. That's order n factorial. It's not very good. Stalin sort is order n because it goes through the list and deletes it if it's not in order. So one pass.
I asked GPT to implement that GPT sort for me.
GPT sort.
Oh god.
Please come take a chocolate thing. I will reimburse myself. I can only. Yeah, help yourself. Okay. Come take from the pile.
I'll take one first.
It's actually
Stalin sort's order n, right?
economics, because it's the same thing if you kill enough members of your beta set, it works.
How do you determine the algorithm is in place?
What was that, sorry?
In place. I mean,
An algorithm is in place if we don't make any extra arrays to sort it. So if we only work with the array that we're initially given with, then it's in place. If we need to make extra things, like use extra memory, then it's no longer in place.
all right.
Gotcha. Yeah.
Thank you.
No worries. You can have one if you want.
How do we calculate the average time?
Calculating it for these.
Because I remember there's the 0.25 something.
Yeah.
That's very good.
To be honest, I've never actually calculated it myself, so I don't know how to calculate it. We normally show it empirically by timing it a bunch of times and seeing how it grows based on that. But in terms of actually deriving it, that's not my forte. I get the computer to do it, or I look it up. Sorry to say. Thank you.
Kind of a question.
Yep,
But
kind of an
I heard
answer.
you know G.
I do know G.
I'm one of her friends.
Nice.
She
G and
was
I are
like-
also friends.
Yeah, she was like, oh yeah, we play board games together, and I'm like,
We do. We play board games every Sunday together when G shows up.
that's really fun. Anyways, I thought I'd say hi.
Hello.
Bye.
What's your name? Is it
I'm
also a letter? That is a letter.
I
Harriet.
wish it was a letter.
It's one of them.
It's a string.
It is. Well done. Good to see you. Hello.
I've got a quick question. If you had insertion and bubble sort, but you didn't know which was which, and you had to distinguish them, what would be the best way to do it? Would you have to swap back first and last elements of each sort?
Like to figure out which one is which.
would you have to like swap the first and last elements and then run the sorts from there?
This is a really good question.
Yeah.
Yeah. Go ahead, have yourself.
I'm just thinking about that because
Yeah. No, that's a great question.
the time complexities are the same.
Are the same, and the number of comparisons are the same in the best and worst case.
Like with bubble
Yeah.
sort, you'd have to make all those passes.
Yeah.
You'd have to traverse it multiple times.
Yeah, I think if you did swap the first and last, I suggest you try this and see if you can do it. I'm not sure. That's a great question.
Okay.
Nice. Good
Thanks,
stuff.
Henry.
No worries.
I managed to get to lecture 2 for last week. So could you quickly explain what O notation is?
Yep. So all the lectures are recorded and posted on YouTube. Big O notation is an estimation of how long the program is going to take based on the input size. So if an algorithm is order n squared, that means if I double the input, then it's going to grow a square of that input instead of growing linearly. So, like if something takes 10 seconds and it was linear, and then I doubled the input, it should take 20 seconds. That's order n. And if something takes 10 seconds and I double the input and it's n squared, how would that go? It would go from 100 to 400. So it's a way of modeling how the algorithm is going to grow. But apologies, it was a 2-hour lecture, and I can't really give a full 2-hour breakdown. But that's the,
I'm going to go over it anyway. I just wanna...
Yeah, that's the short and fast of it.
Thank you.
No worries.
Are we supposed to learn the sorting algorithm by the name? Because it's a lot, no?
There's 6 that we're going to learn.
So quick sort.
Quick sort, merge sort, bubble sort, insertion sort, selection sort, radix sort.
Yeah. So we have to know like what they do by name. Like
Yeah, well, it's-
because it asks me like write a radix or something.
It could do, although I'm trying to figure out how else you would know them, because things have names that we can identify them. That's like the point of a name. So I don't know how else you would know it, to be honest.
Well, I keep forgetting the names of them.
It's okay. You'll be okay. If you play around with them, you'll get a better picture of how they work.
Yeah. I like merge sorts. Oh, that's cool.
Yeah, merge sort's pretty cool. Nice. Feel free to help yourself. No worries. Good to see you. Hello.
You shaking?
I do. What's up?
Oh, just saying hi.
Oh, hello.
Nice to meet you.
Nice to meet you
We've been,
too.
like, in the lecture for a couple of lectures now. Just thought we'd come up and actually like say hi.
Hi. What's your name?
Ollie.
Ollie? Like the skateboard trick.
Yeah, like this. Well, actually Oliver, but people call me Ollie because it's easy.
Because it's
for the skateboard.
because he
Yeah,
invented the ollie.
That's actually
It's named
Nice.
after him.
that's also true.
That's very-
But I don't tell people.
No. It's like John Merge, who you'll learn about tomorrow. You think that it's called merge sort because it merges things. It's not. It is. One day I'll get sick of that joke, but today's not that day. Yeah. Well, you enjoying the course so far?
Yeah, no, I like the course so far. It's
Nice.
good. I like the lectures as well.
Woohoo. That's me. Nice. And you also have a name, I assume.
Yeah, Tom.
Tom.
Like the cat.
True. I couldn't remember if it was Tom or Jerry. I haven't watched it. Nice.
His name Tom because like Tom Cat. Like.
Oh yeah, that. Based. I'm named Henry, not after a cat. Just sort of after the fact that my parents
Henry,
named me
like
that.
the dude, like the Ford guy, right?
Yeah, I am. It's actually me.
Oh, you're looking good for you.
Thank you. I agree. I'm looking good for 2 billion. I think that's about right.
Yeah.
It's an approximation. It's a bigger notation,
Yeah.
roughly. All right. Well, lovely to meet you
Yeah,
too.
good to meet
Feel
you,
free to
Henry.
help yourself to a topic if you want.
Hey, Henry.
Hello. That's my name.
I know.
What's up?
Yeah, and there's something that I discovered that like before we call function by void, like void function and like input, right?
Mm-hmm.
And like when I was doing my lab like last week, I found that like you guys do directly call the function by struct instead of void. So like how it works.
I'm sorry, I haven't really looked at the labs, to be honest, so I don't know if that's... Because I call all of my voids just by the fact that they void.
Yeah,
I thought
but-
C forced you to call it based on what it
Oh
returns.
no, but like your functions are called by void.
Yeah.
Called by struct. Like I mean, like they're not like for the lab last week it's about like calling the. All right, it's actually a code, and you gotta compile it, and it mainly teach you like how to use the sanitizer.
Yep.
But but in the code, I saw like the function is directly struct instead of void.
Yeah.
So, but how it works? Like, what's the difference?
If it's void, it won't return anything, and if
Yep.
it's struct, it will return a struct of some kind.
But somehow, like, if it's void, you can return struct.
If it's void, you shouldn't be able to return anything. So thanks for confirming that for me. You could tell I wasn't entirely confident. Let me just stop streaming, I've realized. Hopefully people are smashing that subscribe button.
You're much taller than I expected.
How tall is you?
This is my first lecture.
Ah.